In this lesson, we're going to learn how a definite integral evolved from a limit of a Riemann sum. So up here in the upper left-hand corner, let's just draw an arbitrary function. We're going to name it y equals f of x. And we're just going to consider some graph that kind of comes in like this and maybe swings around in that direction. Okay, let's say that we're interested in accumulating the area under this curve from x equals a over here to say x equals b. And so we want to make sure and show x equals a to x equals b by building these vertical lines. So we're talking about this space in here. We know what the definite integral looks like for this. Okay, we'll get to that in a minute. So how did they find the exact area under this curve years and years ago? Well, they inscribed rectangles in here, and we worked a little bit with inscribing rectangles in here. So let's come over here and define some of our variables. So we're going to let n be the number of rectangles that we're going to partition inside the region from x equals a to x equals b. So n is going to represent the number of rectangles. Okay, the width of each rectangle, we're going to define that. Well, we want to take the change in the x values. So what we look at is this, that the change in x is equal to the bigger x, b, minus the smaller x, a. That allows us to find this horizontal distance between x equals a and x equals b. And we're going to divide that by the number of rectangles that we decide to inscribe within this region. Okay, now let's define the height of a rectangle. Well, we're working with f of x, so the height of this rectangle right here would be f of a, and the height of this rectangle right here would be f of b, if each of these little thin vertical bars represented a rectangle. So we're going to take the function and we're going to evaluate it at some x, and I'll come back to this in a minute. Okay, let's come back over here and let's start partitioning this region from x equals a to x equals b into just some rectangles. Okay, let's say that I wanted a rectangle that was perhaps this wide right here. So what is the value of this x right here? Well, the value of that x is going to be a, because I started at a, plus, because I'm moving to the right, I'm increasing a increased by, what is this distance right here? Well, that's a change in x. We're going to say a plus 1 delta x. So right here, if I'm going to use right rectangles, I would stop at this little tick mark and I would go up to the function. I'd stop here. And if I'm using right rectangles, the right side determines the height of the rectangle. So if I wanted to know what is this y value right here, because it gives me the height of this rectangle, I would say that this is the function evaluated at a plus delta x. Whatever that x value is, I would insert it into the function. Let's go ahead and partition another rectangle having the same width, trying to do the best I can. What would be this tick mark's label? Well, let's go back to a, but now this time let's increase a by a plus, not 1 delta x width, but 2. So plus 2 delta x's. Create a rectangle from the right side. So what would be this value right here, this height value? Well, you might see that it's going to be the function evaluated at a plus 2 delta x's, since I slid over 2 delta x's from a to get to this input value. I could continue, so forth and so on. That tick mark would be a plus 3 delta x, because I've moved over 3 delta x increments. Likewise, build the right rectangle. We now know what we can label this functional value right here, f evaluated at a plus 3 delta x. So maybe you see the pattern, and it can continue, so forth and so on. So I'm going to come all the way over here and say that I'm finally over here at this partition. What can I call that tick mark? Well, it's a plus, but I don't know how many delta x's I slid over. So I'm going to let the lowercase I, or j or k, in this case I'm going to let the lowercase I represent what rectangle I'm in. So for example, back here, if I added 1 delta x, I'm in the first rectangle. If I added 2 delta x's on the right side, I'm in the second rectangle. Likewise here, I have 3 rectangles, that's why I'm adding 3 delta x's. Well, over here, I don't know what rectangle I'm in, so we're just going to use the lowercase I, and we're going to say delta x times I. That's the input value right there. So I is just going to represent some particular rectangle that I don't know that I'm in. So let's come up here. If I were to build the height of this rectangle, what's the functional value? Well, like in the other previous cases, it's the function evaluated at a plus delta x times I. It might seem strange to put the I behind the delta x because here we put the numbers up front, but it's just kind of common practice to kind of put the I behind the delta x. It wouldn't be wrong to put I in front of delta x to make it look more like this structure, but it's just kind of common practice to put the I behind here. And we could certainly use another lowercase letter like j, k to represent what rectangle I'm in. Remember, n represents the total number of rectangles, but what rectangle am I in? I'm in what we call the ith rectangle. So if I were to build this right rectangle, it would look something like this. Okay, so let's come back over here and finish this statement. So what would be the height of a rectangle that we have based on this function? Well, it's our input value, what x we start out at, x equals a, plus delta x and then I. I put it times I here. So, and I'm going to come down here and define what I is. I is going to be your positive integer, keeping track of which rectangle we're in. Positive integer keeps track of the rectangle. Okay. All right, so now what we're going to do in this space right here is we're going to define the definite integral as a limit of a Riemann sum. So kind of right here in the middle, let's start by talking about what's the area in just one rectangle. Well, we know the area formula for a rectangle is base times height. So let's start with the height. The area in any arbitrary rectangle up here would be the height, which is represented by this expression, times the width. How wide is each rectangle? Well, we have it defined here. It's delta x. So this is height times base. Well, that's all well and good, but I want the area in every rectangle. So in front of this expression now, let's put the summation notation. Okay, I keeps track of all the rectangles we're in, so we're going to put from I equals 1, the first rectangle, to the nth rectangle, the last rectangle. This would sum the areas in a finite number of rectangles. But if we want to find the exact area, we want to inscribe an infinite number. So this is a finite kind of statement of the height times the width. And this adds up just n rectangles. So in front of this, let's move a little bit to the front, and let's put a limit statement in front of the summation notation. Let's say the limit as n goes to infinity, okay, of the summation of I equals 1 to n of all these areas. So all this together is a limit of a Riemann sum. Riemann, you might remember, just means rectangular areas. So all of this is equivalent to the definite integral from x equals a to x equals b of the function f of x with respect to x. Okay, our job down here in these examples is to take definite integrals, such as this, and rewrite these definite integrals as a limit of a Riemann sum. So we're going to look for some structure. So we're going to go from this example down and then over and down. All right, so we've got the definite integral from x equals -1 to x equals 1 of 3x cubed dx. It's equal to the limit as n, the number of rectangles, goes to infinity, of the summation of the areas from I equals 1 to n. And remember, this is the height and this is the width. So this is basically our formula that we're going to be working off of right here. So it'd be helpful to kind of memorize that. All right, so for our example, what we're going to do is, first of all, based on this definite integral, let's define what delta x is. Well, the change in x is b minus a over n. So b is 1 minus -1. We don't know how many rectangles we're going to put in here. We'll call it n. So the change in x is 2 over n. Okay, so now using this formula, working down, notice that I have the same definite integral. We just need to fill this information in right here. So every time we need to bring down the limit as n goes to infinity of the summation of I equals 1 to n. That will always stay the same. And so you can bring it down here too. Where we're going to have to customize based on our integral is what is the representation for the height and the width. So what I'm going to do is I'm going to start with, okay, the height is going to be the function evaluated at some a value. Well, a is our lower limit, so we'll put -1 plus, go back to your formula. Okay, if I'm starting at x equals -1 along the x-axis, I'm going to increase the x values by delta x times I. Well, I know what delta x is. It's 2 over n. So if you replace 2 over n here and multiply it by I, you're going to get 2i over n. And then moving outside this bracket right here, times, you want to keep that in brackets, delta x was again 2 over n. So this expression right here, if you look at the numerator, helps us to identify the difference between 1 and -1. Are we finished yet? No, I need to insert this x value into my function. So we're building. Okay, so right in here, we want to come up with an expression. So what we're going to do is we're going to take this input value, remember this is our x, our new x, and we're actually going to insert it into the function 3x cubed for the x value. So all of this is going to become 3. Wherever you see an x, leave a big parentheses. Go back and put the 3 on here. The dx transcends to 2 over n, so this is times 2 over n. So the only thing that's going to change is we're going to insert this input value in for the x in the integrand. So here I'm going to put -1 plus 2i over n. And that's it. This limit of a Riemann sum represents that definite integral. So some things you can see is that that numerator there, 2, would be the difference between your a and b values. And then it's also 2 over n should be present in the other input value here. So these two should match. I shouldn't have 3n here, or 3 over n here, and 2i over n here. It just takes practice. Let's do a few more. All right, how do we take this definite integral and express it as a limit of a Riemann sum? Well, let's get started with this formula here. Okay, well, we first might want to come over here and figure out what delta x is, which is b minus a over n, so 3 minus 1 over n. Okay, and again here we're going to have 2 over n. Okay, now and here's the height, but for our particular problem, it would be the height of the rectangle would be the function evaluated at a, the lower limit is 1, plus delta x is 2 over n, but don't forget to multiply by I, because I don't know how many increments I've slipped over. I don't know exactly what x value I'm at. So 1 plus delta x is 2 over n, so let's make that 2I over n. And then times delta x again gets replaced with 2 over n. So you can think of this in a big bracket so you don't confuse yourself thinking that you can multiply 2 over n inside here. All right, last step, let's bring down the limit and the summation notation and then customize. Okay, this is our input value. This is our x, f of x. Think of that as f of x. So come over here and find the x that's in your integrand. It's just right here. So I'm going to write down sine. I'm actually going to go to a bracket right here because I'm going to reach inside here, and I'm going to do sine of x cubed plus 2. I'm going to close my bracket. So I've got the sine, and then here I'm going to put x cubed and then plus 2. And then the dx is going to be represented with 2 over n. So right here in this slot is my input, 1 plus 2I over n. And you can see the function in this limit of a Riemann sum. You can see the function sine is over here. This right here is your x value, but we had to start x at 1 because we don't start collecting area until x equals 1, plus some amount over. I see the cube on the x, and then plus 2 was still part of the integrand. And then times 2 over n, which equates to dx. Okay. Oh, goodness. So sorry that wasn't, oh my goodness. So sorry I didn't push that up. Okay, let's come back over here and work on this problem. Okay, how do we take this integral and write it as a limit of a Riemann sum? Well, first of all, delta x is 8 minus 3 over n. So the change in x is we're going to take 5, that horizontal distance, and break it up into n rectangles. All right, let's customize this formula. So what's the height? Well, our a is 3 plus our delta x is 5 over n times I, 5I over n, times delta x again, which is just 5 over n. Not 5I over n, just 5 over n. Okay, there's a plus here. So this is our new x value, our input value that goes in for this x right here. So let's take the integrand. Let's write the square root. We've got 1 plus, where you see x, put a parenthesis. Okay, and I'm going to close that right there. And then don't forget, if you can squeeze it in over here, it's times 5 over n that comes down. So right here is our x, and our new x is 3 plus 5I over n. Some might say that you could collect 1 and 3 and make it 4, but then you kind of almost lose the perspective of the structure that this one, okay, was underneath the radical here. If I collected and got 4, it might be misleading. So I would just walk away and not clean this up. Okay. Bottom right example, how do we express the definite integral from x equals 1 to x equals 4 of natural log of x dx as a limit of a Riemann sum? Okay, let's customize the a and delta x values. Lower limit's 1 plus, oh, I forgot to find delta x, b minus a over n. So delta x is 3 over n. So plus 3I over n. And then you can do a bracket if you want, times 3 over n. Okay, and so we want to go into the function, which is our integrand right here, and this is our new x. So we're going to have natural log, we'll have a parenthesis. where x is, we're going to replace it with 1 plus 3i over n. And then I'm going to go times 3 over n. And again, we're not multiplying these two together, so maybe a bracket would be helpful to distinguish between the height and the width. Okay, we're going to practice a few more problems. There is a back to these notes, but we'll do those together at a later time. But here, I wanted to do some more practicing of writing a definite integral as a limit of a Riemann sum. So if you want to just write these 8 problems down as we go through them, the worksheet's not that critical. I mean, if you have capability of a printer, sure, go ahead and print it, but otherwise I wouldn't worry about that. Just write the 8 problems down and we'll build the limit of a Riemann sum. Okay, here's a definite integral. What I would do in this little space right here is I want to define what delta x is. So that's going to be 6 minus 0 over n. So delta x is equal to 6 over n. Okay. I might also get the notation for the y value. So I'm just going to think ahead into that formula of the limit of a Riemann sum, remembering where this is a plus delta x times I. Well, in our case, a is 0, so 0 plus delta x times I, 6i over n. Is it necessary to have the 0? No, it's just a visual that that's your a value, and it matches up, but you don't need to do that. All right, limit of a Riemann sum, always first. So the limit as the number of rectangles goes to infinity. Summation, you could use I, j, or k. I equals 1 to n, keeps track of the rectangle. And then we want to do the function evaluated at this input value. See if we can kind of take away some of the scaffolds. So let's go to the integrand. I'm going to go straight to the integral. Underneath the integral, I'm going to have 2 times x, and then I have the plus 1. This x is reserved for this new input, so that's going to be 0 plus 6i over n. And then I want to multiply this height times 6 over n. Remember, there's no I here in the width, delta x. It's just in our input value. Okay, if you feel comfortable, I would stop the video and try and do as many of these as you guys can, just for some extra practice. So number 2, delta x is 3 minus negative 2, or 5 over n. So what's our new input value? Well, we don't start accumulating area until x equals negative 2 plus 5i over n. Okay, what do we do here? We look back over here at the integrand. I see x squared minus 3. I might put this in brackets, and I'm going to multiply it by delta x, which is 5 over n. Last thing, take your new x and insert it into your parentheses. No cleanup, we got enough to deal with. Let's write this definite integral as a limit of a Riemann sum. So delta x is 6 minus 1, or 5 over n again. So what's our functional value? Well, our new x is going to be 1 plus 5i over n. All right, so we're going to take this new x and we're going to insert it in that slot right there. So I'm going to go ahead and build 3x minus 4, but leave my x slot available. Might do some brackets, and times delta x. Okay, number 4. You try some. 4 minus negative 2 is 6 over n. My first x is negative 2, plus I want to increase it by 6i over n widths. Okay, right here we want the height. That's determined by the function, so it's x cubed. And then I'm going to do times 6 over n. It's your new x. your new a plus 2I over n. Build your square root. Underneath there, I see an x, big parenthesis. That's your square on your x, plus 1 times 2 over n. Insert. And we have the limit definition of a Riemann sum. We didn't see, I don't think in any of these definite integrals, a couple of x's, meaning what if this was 4x cubed minus x? Well, then right here, I'd have to have minus and another parentheses where I'd have to insert that same input value. So that didn't work out on any of these. I almost wish it did, but I'm hoping you see if you have multiple x's here, then over here you have to insert multiple input values like this. All right? So hopefully you got the structure.